Hi, I'm Andy Trudick, and today we're going to be talking about a new approach to artificial intelligence inferencing with Sagence, formerly known as Analog Inference. And this is part one of a two-part series, and Rich Terrell will take us through a presentation of the company's newest technology that it released on November 19th. Go ahead, Rich.
So thank you for joining us today. We're excited to tell you what we've been up to for the past several years and reveal the core technology and the intent of the company. We've been working as most folks know in a quiet mode, but now we're able to talk about it and quite excited. But inference is not well served, as evidenced by the lack of the broad deployment. We just don't see it going out into what we've been promising as an industry for some time. And so we've taken some time to sort out why we think that is, what are the issues that limit it, and bring to bear technology, innovation, invention to solve those key problems. And it comes down to essentially using the right tool for the job. And so what we have done is we have harnessed analog compute and memory in a core technology integral to our chips and our systems, specifically to solve simultaneously the power, cost, and performance issues that we see as impeding the broad deployment and scalability of AI, and in a couple of different sectors, which we'll talk about, both computer vision as well as generative AI going forward. About the company, so a snapshot of who we are so that you get a calibration. We are a startup. We have funding, and we're started by some of the luminaries in industry. You can see there in the lower right that set a challenge ahead of our CEO, saying, go solve this problem, go fix this inference problem and find a new way to solve it. And so you'll see as we get into the technology, it's not about incrementally doing better at what everyone else is doing. It's fundamentally taking a different look at it and changing the structure of the solution to fit the needs for that. 6 years old, started in 2018, and really looking at developing a persistent technology that solves avant-garde problems of today, as well as we believe perceiving the problems that confront in the future, so that we make sure that we have solutions that go well into the problems that we see in computing, even over the horizon. This will be, of course, speaking to the choir. You've been reading the press and researching and analyzing it, but it's interesting what Sequoia said a couple of months ago, I believe, when they said the industry needs to generate $600 billion a year to justify the infrastructure costs going into the generative AI. That's a tremendous amount of revenue. And that's from the end user revenue. That's collecting it from lots and lots of people. And there's not a lot of clear paths forward on how to do that. And in fact, it's really started to slow down a lot of the innovation and deployment, especially on the training and the creation side, because people need to look at how are we going to harvest the revenue from the inference side of it. And NVIDIA came out and stated that the revenue that's really being generated, it's going to come from that inference side, and in large measure, the super majority of it. So the challenges that are faced, in particular with generative AI, they're really twofold. They cost too much to run, and they consume too much power when they are running. And unless you simultaneously solve both of those challenging problems, you're going to be limited in what you can do in terms of the deployment, and it's going to be hard to reach those revenue goals to really justify all the investment that's been made. As we looked at the problem, what emerges is if you use the classic general purpose computing architectures, the GPUs and the CPUs, to do the inference side of AI, you're probably using the wrong tool. The AI inference, it's not a general purpose computing problem. It's not about a random code and random algorithms that run on demand. Inference is actually very predictable, very programmatic. We know exactly what's going to run, when, where, and how, and we know in advance half of the data that's going to be used in the operations. And that speaks to a different type of computing hardware. And so as we looked at what it was that was limiting the deployability of inference and getting into the broad volumes that people have been promising, the cost, the power, and the complexity of doing it, we wanted to solve them concurrently, not just incrementally to fix one and then have issues with the other. What is it that it takes to do that? And what's emerged is that when you move into the in-memory computing and you do it with analog, which is what we're doing, you really broaden that economic viability window that we believe is necessary in order to get to the the promise and the demand that's been offered out there by AI for quite some time now that we're going to be able to deliver products to solve these problems. We're excited to talk about the how part of it. But we started from the business. What is it about the business and the hardware and the solutions that are out there that simply had not been successful to date? Was switched from doing a classic von Neumann approach to the computing problem to doing an in-memory computing solution. If we look at inference, the issues and challenges that arise from a digital approach to it using a finite number of arithmetic units is you get into a scheduling and traffic problem. You're moving a tremendous amount of weights in and out of or into the computing fabric and spending a lot of time scheduling where things are going to be. And our founder, Vishal, elected to use a different approach. He said, what if we could put all the weights on the chip and use flash memory to do that? So if we can run the flash memory in a multi-level mode, storing 8 bits per cell, that automatically reduces the complexity of the problem significantly. An 8-bit integer weight in a neural network with SRAM takes 48 transistors. Plus, it's one transistor to do the same. And in addition, it's non-volatile, so it's not dissipating power while it's holding that weight. So that solves one big part of the problem with the scale up of inference. The other is, how do you do the arithmetic? And so what we've also done is we've elected to operate those flash cells in the analog mode. So we're not using them strictly as storage elements. We're also creating multipliers. So when we store the weight on the floating gate, and we convert the incoming activation data, whether that's video or web clicks or tokens, and convert it into analog and present it to essentially a really wide flash word by simply reading that wide flash word, that column that you see on the screen, and then collecting the data that comes out. We've implemented the multiply accumulate without any of the complexities of a classic digital Mac unit. And that's what gives us the significant power savings, because we've pushed everything into the analog realm and we're operating it, in this case, in deep subthreshold. Essentially, we're modulating leakage current to do the arithmetic inherent to the vector matrix multiplication that's integral to AI and in the inferencing task. This illustrates a bit more on the detail of what we're doing with that. I like to emphasize the deep subthreshold computing. This is a significant component of what differentiates our technology. We believe that compute to memory, in-memory computing, is essential going forward as the solution for the challenges that the industry faces. We're choosing analog with flash. We believe there'll be other technologies that come to bear as well, because it's a natural way to solve these problems. And what we're able to deliver in our technology is 100 TOPS per watt. That's in the computing fabric. And that's where these substantial power savings arise, because we change how we're doing the arithmetic, we change how we're implementing it, and we also provide a path forward for the scaling, because of course we'll be able to take advantage of all the innovations that go forward in the processing technology. So we like to call it true in-memory computing. We're not near the memory, we're not close to the memory. Our memory does the computing, and that's the leap and the jump forward that's necessary to get to these advantages that we've described. So those are impressive numbers. What can you do with it? We're showing here a proposed product we're working on right now, and a tremendous amount of concern about how do we harness the costs, both the acquisition costs and the operating costs, to run the generative AI models that are coming out and that are seeming to get bigger and bigger all the time. And we're taking the approach of a chiplet technology to stack up our compute and memory analog slices, you can see on the left there, onto mezzanine dies and build interposers with them. So this gives us a modular approach to be able to accommodate whatever complexity or size of models that arise in the future for the large language models, the current as well as what's projected, and to build systems that are able to handle those using this exact same in-memory computing approach. Our analysis of it shows that about 95% of the math and computation that's done in the inference side fits nicely into our analog computing model. And then the rest would be pushed into that digital process that are there in the middle. So this is the conceptual diagram that we're working from today. Let me show you what the metrics would look like. Now, we have our chips. They're in our lab. We're bringing them up. We'll be announcing products next year. This is a technology announcement today, but using that product chip that we have for our first products, we've been able to get some initial metrics out of it and to project what that would look like when we build a large language model specific system. And so in this case, we're comparing a Llama 2 70 billion parameter and normalizing the performance at 2/3 of a million tokens per second and comparing against NVIDIA H100. That's the GPU that's in the mainstream demand right now. It's where the metrics are best known about it. Of course, they have newer models and we'll have more into the future, but this just gives you a baseline comparison that if we take a normalized performance number, what would it look like implemented for them, power, performance, and volume and cost, and what would it look like for us? And this is showing we're taking their published numbers, we're taking our prospective simulated results from our silicon, our system analysis. You can see here the substantial savings that you're getting. And these are concurrent savings. These aren't trade-offs one against the other. You get them all simultaneously. So the lower power, the lower price, as well as the smaller volume, because we're able to compress, if you will, into much smaller space by storing all the weights of the model directly into our chips. So we're able to put, in this example, a single rack of servers where they would be 22 racks or so to achieve the same performance. So this is the type of differentiating substantial advantages that you see when you take a different look at how you're going to implement on that inference side for the large language models. The natural and important question to ask then is, okay, this is a great technology. If you can get this working and it seems to be a natural fit, how do you program it? And historically, software has been the Achilles heels for many of the startups that are trying to come out with a new computing architecture. And our staff, our employees, our team is very well aware of this, having been at many of the companies that did exactly this, bringing out new technologies like programmable logic, like multi-core. And so we started with the software. We took an investment at the beginning to say, how will we make the tools so that they're first non-intrusive to existing design flows? So we use standards-based interfaces. And then second, how do we make it so there's a low friction of adoption to go through for customers to integrate their existing solutions today and not have to go and do a bunch of changing around it? And so we've been working on them from the onset of the company and have been able to use them in parallel, hardware, software co-design, if you will, making sure that as we come up with a new computing architecture, can it be programmed? And when the code developers develop a new algorithm, the hardware guys can implement the features necessary to do that. And so we're showing here a fairly high-level view of it, but we like to emphasize on the left, the trained network. We start with the quantized trained network out of the existing design flow, imported into our tools, and we do the analog quantization within our software suite. We don't require people to make changes to their design or their training approach in order to take advantage of the performance and power advantages that we're bringing. And so we're quite open. We tell people what's happening, but we don't require them to learn some intricate low-level details in order to realize the benefits. And then importantly, we're not just making accelerators, although that's our product that we ultimately sell as hardware. These have to go into systems. And in order to do that, you need to have both those blocks of code shown there, the runtime code, how your hosts and the host software interfaces to the accelerator, and then the firmware that runs on our accelerator itself. Both of those are generated concurrently by our software to ensure that the system, when it's implemented, will run at the highest efficiency and it's non-intrusive to the existing infrastructure, whatever that happens to be, if it's a VMS video management system, a point of sale, inventory management, or some sort of security application layer. We interface to that by providing the source code so that it can be readily adopted by our customers without a lot of intrusion to their existing implementations. A word about the team. This is hard engineering, the type of work that's needed to be done to harness the flash memory cells, to run them in multi-level with 8-bit, to run them in deep sub-threshold, to build architectures that are highly efficient, both in terms of the silicon utilization and then the software mappings. The average tenure of our team is 25, 30 years in industry. Doing this from the very low level at the cell design all the way up into the system and application levels. So we're fortunate to have brought together the right team to bring this about from all of those perspectives, the circuits, the cells, the architecture, the chip, the systems, and then all the way into the business side of it, because the business models of deploying AI, it's not just simply selling chips and boards. It's much more comprehensive than that.
Thanks so much, Rich Terrell, for that presentation. Now I do have a few questions, so we'll continue our conversation in part 2. Click the video on the screen or scroll down to watch it.